Today in Math 30-2, we're going to look at topic 6.2 and we're going to examine the characteristics of exponential functions. First of all, we're going to take an example. And in this example, we're going to talk about how many times you can fold a piece of paper. When we start out, we're going to have no folds and there's going to be one layer of paper. Now after we fold it once, that'll create 2 layers of paper. If we fold it again, that'll create 4 layers. If we fold it again, we'll get 8, fold it again 16, fold it again 32, fold it again 64. So by the time you folded one piece of paper 6 times, you're going to get 64 layers of paper. Now, if we look at this as an exponential function, it'll go by y equals a times b to the power of x. And actually, this graph is 1 times 2 to the power of x. And if we graphed it, we could start by plotting our points. When x is 0, y is 1. That's the first point. And when x is 2, y is 4. That's that point way up there. When x is 1, y is 2. Now I can draw the graph through those points and you can clearly see that it's an exponential function. Let's go to another one. Let's say y is equal to 4 times 3 to the power of x. Well, let's plug in some values. First of all, when x is 0, what's y? Well, when x is 0, I'm going to have 4 times 3 to the power of 0. Well, remember that anything to the power of 0 is equal to 1. So 4 times 1 would be 4. Therefore, our first ordered pair, when x is 0, y is 4. When x is 1, y is going to be 12, because 4 times 3 to the power of 1 is 4 times 3, which is 12. Lastly, when x is 2, 4 times 3 to the power of 2 is 4 times 3 squared, which is 9. 4 times 9 is 36. Now let's plot these 3 points. If you go up by tens on the y-axis, you can plot 0, 4 very low, and you can plot 1, 12, and then you can plot 2, 36. So that's what our graph's going to look like. It's going to go through those points. Next, let's have a look at this. Notice that the y-intercept is at 4, and the first value is y equals 4 times 3x. And our first one, where we have y equals 1 times 2 to the power of x, our y-intercept is 1, and our first value was 1. Well, if we take our standard graph of y equals a times b to the power of x, what we've noticed so far, what it looks like, is that a is our y-intercept. What's b? Well, we'll come back to that later. But let's keep going and we'll see if we'll do a couple more examples and see if this holds up. Let's look at y equals 4 times 1/2 to the power of x. This time, my b value is small. It's only a half. So let's see what happens when we graph something like this. Well, again, when x is 0, we're going to get 4 times 1/2 to the power of 0, which is 1. So it's going to be 4. So again, yes, when x is 0, y is 4, and that's our first value, our a value. And then when x is 1, we're going to get 4 times 1/2, which is 2. And when x is 2, 4 times 1/2 squared, and 1/2 squared is 1/4. 4 times 1/4 is 1. Then if we plot these points, you're going to see it go down over time. So now what it's going to look like is something like that. So what can we say about b? Well, so far, it looks as if in the first graph b was 2, second graph b was 3, and notice those are both increasing. So we can say if b is greater than 1, our function is increasing. But if b is less than 1, but it's still going to be bigger than 0, so we got to write that as b between 0 and 1. Our function is decreasing. Or it looks to be anyhow. Anyway, those are the general patterns that we kind of see. Let's do one more to see if this holds up. How about y is equal to 9 times 1/3 to the power of x? This time, what we're going to do is we're going to plot our x and y's. So if x is 0 again, 1/3 to the power of 0 is 1. So when x is 0, y is going to be 9. Now we're going to do all the work this time, just to show you where this all comes from. That's the ordered pair of 0, 9. In the next one, 9 times 1/3 to the power of 1 is 9 times 1/3, which is 9 over 3, which is 3. So we get the ordered pair when x is 1, y is 3. Lastly, when x is 2, 9 times 1/3 to the power of 2 is 1/3 times 1/3, which is 1/9. 9 times 1/9 is 1. That gives us the ordered pair x is 2, y is 1. When I graph this now, we've got x is 0, y is 9. When x is 1, y is 3, because we're going up by 3's there. And when x is 2, y is 1. And we can put those all through and get that kind of a graph. Now, for all exponential graphs, it appears that the number of x-intercepts, well, there aren't any. The number of y-intercepts, it appears that there's always going to be one, and it's going to occur at point A. Next, our graph seems to move from quadrant 2 to quadrant 1 in all cases. Our domain appears to always be x can be any real number. And our range appears that it's always going to be greater than 0. But there's another value we want to look at, and that's going to be how to get the b value from our table. If we look at and go back, we can say if term 2 in our first graph was 4 and term 3 was 8, and I divided those two, 8 divided by 4, I get 2. That's our multiplier. It's going up by 2. Every column, or every number in the second column is times by 2, and that's our b value. Well, let's look at our second graph. It goes 4, then 12, then 36. Every number is being multiplied by 3. So it appears that b is our multiplier. So lastly, your assignment, do page 346, numbers 1 to 8.